Good afternoon. Today we will learn format string vulnerability as an application of the sequential and arbitrary read and write. Let's do a little recap on arbitrary read first. This capability lets attackers obtain some data in the program, and this could leak the address such as or stack cookie, etc. So it helps writing exploits by bypassing defense mechanisms such as stack cookie. So we can directly leak the cookie value, and also breaking the ASRL, we can leak some of the meaningful addresses and then calculate all the relative offsets for the other targets. And then bypassing these two will allow us to also bypass DEP by building a ROB chain from the leaked information. And for the arbitrary write capability, this lets attackers change data in the program. It could be arbitrary, meaning that at any kind of address, or it could be sequential, which alter the data adjacent to the object. Yeah. And using this, we may alter the control data such as a return address, frame pointer, or entries in GOT. Yeah. Then we can run arbitrary code. And today we will learn about the format string vulnerability, and simply we will learn some weird use of this printf function. I'm sure that all of you guys are familiar with this printf function, and this function is mainly used for writing a format string. As a coder, we use such functionality every day for printing out program data in certain format. And the interesting thing is that we can turn the vulnerability into sequential or arbitrary read or write primitives. So the vulnerability allows us to leak important data from the program and also achieve the arbitrary code execution, say running bin-sh. And the vulnerability itself is very simple. Take a look at here. So this is the regular usage of the format string. So if we just run this program, then it will fetch the 1 for %d, print 1, 2 for %x, so print 2, then ASDF this string as a %s, so printing ASDF, and then 3 for %p, so it will print 0x3. Yeah, %p is printing the number in the address format. And the vulnerable case is this one, so printf buffer, just using the buffer, not using the constant string that has the format string. Yeah, so this indeed should have the similar impact with this one. So this one, it prints the buffer as a string, and then it also prints the buffer as a string. But actually not like that. Think about the case that we put lots of p's in the buffer. Then what this printf will do? So in this case, it will just print out %p as a string. But in this case, printf will interpret these as something like this kind of directive and try to fetch the argument from the stack and then print out. So it actually prints out some of the values from the stack, and that's the start of the format string vulnerability. Then let's dive into the details of the format string vulnerability. So the vulnerable case is when the attacker injects directives such as %p, %s, d, x, yeah, those kind of things into the format string itself. So it looks like something like this. Yeah. And then this can be exploited as arbitrary read and write. And this is the basic use case of the format string. So this is not an attack at all. So we can use the format string like this, and mixed with some of the strings and the directive, then it will match the type and also the length for of the output to prettifying all the output from the program. And then it provides some of the easy way to construct the formatted string. So we can use directive for a %s for a string, %d for a decimal integer, %x for the hexadecimal integer, and %f for the floating point number like this, and also %c for a character, and %p for like printing the value in an address format. So the one interesting thing is like a %p is actually similar to the %x, but the different thing is like a %x is like the printing the number in hexadecimal in like a no format, but if you use a %p, then like it will be printed as a 0x something, yeah, and then in hexadecimal. So it prints out some of the addresses, yeah, in the printf. And we use this function in libc a lot. So for example, not just for printf, in sprintf, vsprintf, smprintf, and lots of like it's similar to the printf function, and also for scanf, yeah, we use this kind of a format string. And not just for the C or C++, even in Python, we have like similar features like this, and also in Java, we have the format string like this. This is convenient. Yeah. And an interesting thing about this printf function is that this function is defined as to receive the variable number of the arguments. That is, it is defined like this. So only requirement is that we have a restriction on the first argument. It should be a character pointer, but for the others, we don't have any kind of restrictions. This is because by the nature of the printf's usage is printf is designed to receive multiple arguments. So for example, if we have one directive, then we will have 2 arguments, 1 additional argument. But if we have 2 directives in the format string, then we should have 2 additional arguments, 3 arguments in total. 3 directives, then 4 arguments. And then if we have an n number of like the directive, then we need to have like an n number of additional arguments for the printf. So we need to put like any number of the arguments to the printf. So this is why it is defined as a variable argument like this. Yeah. Then how such variable argument passing works. So actually printf did nothing for this, and it's very simple. How it works is very simple if you take a look at the stack configuration. So take a look at this diagram. Suppose this is the stack configuration of the printf. So this is the stack frame of the printf, and then save dbp and the return address. So the first argument of the printf, the format string, will be here, and then additional arguments will be placed at this region. And then suppose we make a following function call, a printf %d 1. Yeah. And in this case, we have the first argument, the format string is a %d, and then second argument as 1. Yeah. And then internally, the printf emits a %d. It will increase the argument index and then fetch 1 from here. And then for having 3 arguments, what we need to do is like as a function caller, we will put this format string as a first argument, and then second, third, fourth argument as a 1, 2, 3. These 3 additional arguments corresponding to %s, %d, and %c. And then whenever printf processing this format string, it emits s, then it will fetch the first argument and then increase the argument index, and then %d. So now the argument index is 2, so we will fetch from here and then increase the argument index. So when we emit %c, then it will fetch from the argument +3. Yeah, here. Yeah. So what printf will do is like whenever it emits the %, then it will increase the argument index starting from 1, 0, and then after emit %s, increase 1 and read from here. After emit %d, increase 1, read from here. After miss %c, increase 1 and print from here. Yeah. It's simple like this. So printf don't need to do anything about the variable argument kind of thing. So whenever it emits the %sum of the directive, then just increase the argument index and then fetch that. That's it. Thanks to our like the x86 stack and then calling convention. Yeah. Then what will happen if you run the following function? So for example, put a format string directives, but not supplying any kind of the additional arguments to the printf. This is completely legit in the C syntax because it is defined as having a variable arguments, so we can omit that. So this is actually the valid syntax. And what will happen? We already have experienced this kind of the condition. So in challenges such as ASRL2 and ASRL5, do you remember this kind of the code snippet? What kind of the output this printf prints out? So it does have like lots of %p's, but it does not have any kind of the additional arguments at the end. And it printed out some of the values from the stack in hexadecimal because we used a variable, a directive %p, and it prints out the values in the stack, even if we did not supply any kind of the arguments. So that is, suppose we call a printf with 3% p's to reduce the complexity of the problem. Yeah, and then our stack will look like this. And suppose we didn't supply any kind of the arguments, so we don't know the values, so just put it as an x, y, z. And then if we run this, then printf will, for the first %p, it will print out xxxx, this data. Because how it works is like after emitting the %p, increase the index by 1, and then read this. And then for the next %p, increase index by 1, and then print this. And then print z. Yeah. So basically, by controlling the directives, we can actually leak the data in the stack. So you can use this as a sequential read capability. Then please take a look at the following example code. So it gets info from you and then just supply that into the printf. And if we supply lots of %p, then it will just print out some of the values in the stack. Yeah, like this. And at this moment, let's take a time to learn more details about the directives of the format string. So we have %d, this is an easy one, so it expects an integer value and then print out as a decimal number. %x, it also expects an integer value, but it will print out that in a hexadecimal number. And then %p, it also expects an integer value, and then it prints out that it has like a hexadecimal number and prettified with the look like a address. So the difference is like the 0x will be attached over the output of the %x. And then the different thing is a %s. So all these three directives are expecting an integer value, while %s expecting the address. So address should be the address to a string, which is a character pointer, and then the printf try to read this address and then get the string content and then print out that. So it involves the dereferencing of the pointer. So the important thing is like while bxp does not do any kind of dereference and then treating all the arguments as a value, but the %s will apply dereference for that. And then there are some more important syntax that we need to learn before using the printf for the format string variability, and that is %number, $number, and directive. So it could be a little complex, but so I managed it to colorize all the thing, and then the after %, if we have a dollar flag here, then the number in between the % and the dollar flag means that the argument position. Yeah. So previously we just learned that if we do %p, %p, that then it will just fetch the argument mechanically. So increasing 1 and fetch this, increasing 1 and fetch this, something like this. But actually in printf we can choose the location of the argument. For example, if we put the $3p, then it will fetch the third one, not the first one. Yeah, so we can do that kind of control. So in this case, like if we put 1, then it will fetch the first additional argument. And then if we put 2 in here, then it will fetch the second argument from the additional 1. So we can fetch any kind of we can supply any number to choose which argument to use. And then after the $sign, the numbers are like indicating the length of the output format. So 08 and D means the decimal integer, and 08 means that regardless of the the data itself. So for example, data value is 1. Suppose the data value is 1, and then even though the length for printing that value 1 is just that we require just 1 character, and then it will pad with the pad as 8 characters. So it will always printing out the 8 characters, but if we remove this 0, then it will it will print out space, 7 spaces, and then number 1. But if we put 0, 8, so this 0 means the 0 padding, so it will be padded with the 0 and then printing 8, so it will be 8 characters, so 7, 0, and number 1. Yeah. So there's some of the syntax that we can utilize for controlling the number of characters that we need to print, and also the which argument we want to use for printing that directive. So I prepare several examples. So in this example, so printf %2 something. So %2 means that they're not using the first additional argument. It will use the second additional argument. So it will print a 13 as a decimal number, but will be padded with 0 in length 8. So it will print out 6, 0, and 1, 3. And in this example, it will print out 0x and something. %3 means 1, 2, 3. Use 14 as the value, and then x means that it will print out hexadecimal integer. So 14 as a hexadecimal integer is a d. Yeah, so it will print out d, and then padded with 0 and length 8, something like this. And then this 0x comes from the heading. And then, like, suppose we run the printf %3 $20s. So this 20s is like the printing the string in the length 20, but the 3 means that the 1, 2, 3 are using this as the argument, but the %s expects an address. So the number 14 is not the valid address at all, so it will generate the fault. And in the last example, %4 $20s. So it will print out ASDF, but it will have a little bit of padding, so to fill the entire length as 20. So it works something like that. So this will determine like the total length of the printing this directive, and then this one. So the number between the % and $. Yeah, it will determine which argument we will refer to. So 1, 2, 3, 4. So for the first format string challenge, fs-read1, you can check both the code and output. So if I run the program, it will run main and then input function, and then it will generate some random number and hide that random number in a local variable somewhere in the stack. Yeah. And then it will ask us typing some of the name, and then so this part. And then for the name, we can supply up to 63 characters, so there's no buffer overflow vulnerability at all. And then it will printf hello, and then printf name, the input buffer itself. So there's a format string vulnerability here. So that's why, although I put the %x here, so it did not print out hello %x. It printed out hello, interpreted %x, some of the value in the stack by the printf. So this is the result of the actual sequential read on the stack. And then it asks for like the guessing some of the random value for us. So we can type some of the hexadecimal number here. And then it goes to the variable order, and then this order must be the same as this random number, which we don't know. Then we can get a shell, otherwise we will get exit -1. So in this case, can you lick the random value and then always make the correct guess? That's the challenge. And yes, you can. And please refer to this kind of the diagram. So your stack will look like this. And then you can put any kind of the format string at here because you control the format string by the input. Yeah. And then you can put any kind of format string, and then random is somewhere in the stack. So in this example, it's in the distance 3. So if you just apply 3%p, but at the third one, you can see the random value. Yeah. So you can see the random value at here and then make the perfect guess. That's the challenge. So this is the example. So the vulnerable part is that the printf uses the format string that controlled by the attacker, and then we can type lots of %p's, and then it will print out. So printf will work as if there's additional arguments, although we didn't put anything. And then it will eventually leaks the value in the stack, and then eventually leaks the secret value. So this is the one instance of the execution with the lots of %p's. And then can you see the random number here? So the original random number was this one, but I just guessed at the 1, so it ended up with the exit -1. But from this output, you can see that the random value is here. So 1, 2, 3, 4, 5, 6. So for the 6th %p, it actually leaked the random value. And then if we pick this number for this guess, then we will always make the perfect guess. And then how and why it works. Let's take a look at this kind of the case in detail. Yeah. So this is the disassembly of the format string read 1 challenge, and then from the read random call. So after calling the read random, it stores the return value, the EAX, to the local variable EBP -50. So the random value is at the EBP -50 in the stack. And then it will call the stack. So our stack configuration would be something like this. So this is the saved EBP. So this is where this happens. And then it subtracts a 54 ESP. So the ESP will be down like this. And then this is the EBP, EBP plus -54, and then at the EBP plus 50, -50, we have a random variable. And then they are subtracting of the stack and then push for the printf, so the stack will be configured like this. So for the first %p, it will print out this, second, third, fourth, fifth, and then sixth one. Yeah. Then we can see the random variable. So you can actually calculate the argument distance from the printf call and to the random variable, and then you can actually make the perfect guess. For example, $6p, then you will always see the random values printed at here. And the next challenge, format string read 2, it asks for the same thing. So it asks you to guess the random number. But the problem is that, so right now, so we have a EBP and then return address at here, and then we will have the random value at here. But our printf call starts at here, and then we have a big chunk of the data, more than like around the 600 bytes. Around the 600 bytes, but %p in 32-bit can only print out 4 bytes. And then, so in this example, we can only supply 63 characters at max, and we can only put like a 31% P's. That means we can only print 124 bytes, but the distance from here to the random number is around the 600 bytes. So just using %p, you cannot you can print some of the data here, but it cannot go over this kind of a big buffer and then leak the random number. That's impossible. So to do that, we can use this kind of the $flag directive to choose the argument. So we can skip the uninterested part of the stack, and then we can directly pinpoint the argument number. So if it is long, then it could be a big value, so 150 something. But if it is short, then it could be like 20, 30 something. Yeah. But in this case, like we need to skip like around the 600 bytes and then like point a random number and store it into the stack. So how can you do that? Is that you can set the breakpoint at the printf. Printf the format string vulnerability, and then you can identify like where will be the location of the %1 $p. And then you can also get the address of the random value. And if you subtract these two addresses, then you can get the distance from like the first argument and the random value, and then you need to divide this by 4 in like the 32-bit and divided by 8 in 64-bit, because the unit of like the argument is 4-byte in 32-bit and 8-byte in 64-bit. So if this value is 77, so if you apply $77p, then that will print a random. So you need to figure out like the actual distance to solve this challenge, and then if you match the correct number, then you can exactly print out the random number by skipping all the unnecessary part of the in the stack. So before doing this, please practice yourself with the %6p, %7p, and then try like the bigger numbers, and then like to be accurate, please use GDB to calculate the accurate address accurately, and then like you get the argument distance accurately too. So now we just learned how to convert the format string vulnerability into sequential read. So we just read some data from the stack, which does not require specifying an address. So what we did is by climbing up the argument numbers, we can leak the data in the stack. And we can also use a dollar flag to skip some of the unnecessary stuff in the stack and then leak the data, and we can do that. But how can you convert this variability into arbitrary read? So right now we can do sequential read, but we cannot specify some of the specific address. So for example, if we want to leak some of the data in GOT of some of the program, then we cannot do that right now. And we can do that. And before getting into that, let's check about the directives again. So the difference between these two sets of the directives, X and D and P, they are expecting an argument as an integer value, and then just to print that in the format. And then for %s, this is a special one. It will regard the argument as a pointer, and then try to dereference that address, and then print out the contents as a string. And the last one is the more weird thing. %n is writing a number to the address supplied by the printf call. And then let me give you some of the examples of the %n, because like you guys are familiar to %s because you have used it, but I believe most of you have never used the %n. Yeah, but we will use this a lot, so yeah, we need to learn that. So %n is for storing the number of the printed characters to the variable. So for example, suppose we have an integer variable I here, and then if we make a printf call with the ASDF %n, and then supply the address of the I. So we need to supply the address, then like printf will dereference it, and then put the data in here. And then it will put the value 4 to I, because it printed 4 characters and %n. So %n does not print any characters, but it will record the number of characters printed right before meeting the %n directive. And then if we do %12345x %n, then although like the value itself is 1, so this directive will print 1, 2, 3, 4, 5 characters. So there's no padding at all, so it will print out like the 1, 2, 3, 4, 4 of space, white space, and then 1. So it will entirely print out the 1, 2, 3, 4, 5 characters. And then if we run %n, I will store the 1, 2, 3, 4, 5 because we printed out this much characters. Yeah. Then let's go back to the stack diagram we had. So in fs-read 1, we have the following stack configuration. And then the printf argument is starting at here. Yeah. And then there will be some of the random value here, and then our buffer is also in the stack. Yeah, then something like this. And then if you inject lots of p's, something like this, you will see an interesting value here. So not for the random value, this one. Yeah, a more interesting value is this one. The reason is the value is 25, 70, 20. 25, 70, 20, 25, 70, 20. These are keep repeating, and that's actually the ASCII code of the 25, 70, 20, 25, 70, 20. So this is actually the input that we gave to the program. Why? Why do we have like this kind of thing in our output? This is because the buffer we are using is also in the stack. Yeah. And then we know that the %p, 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 so 6th %p will print out the random value. And then that random value was at the EBP minus 50. And then our buffer is at the EBP minus 4C, like this, so right above the random value. So at the 7th argument, yeah, we will have like a %p space %. So 25, 20, something like that. So 25, 70, 20, 25, yeah. So we have that in the 7th argument. That's why. And then can we exploit this for the arbitrary read, to have the arbitrary read by exploiting the format string vulnerability? And yes, we can do that. And please take a look at the following example. Suppose your target address is 804A010. So this is one of the GOT of the printf in the real program. And then if you want to read this address, put that in your buffer. So you can do that by like putting this address like this, and then after that you can put some of the directives. So if you put this address and then %7$p, because this value will be shown at here like this, and then 7th argument is the integer value itself. So this %p will print out the 804A010. So please test it first. So you need to see that your input as the like hexadecimal integer here. And then if you change this p into s, %s, this will dereference this as an address and go to the address and then get the data and then print that out. Yeah. So by supplying the address in the buffer and then by choosing that as an argument and then running printf with %s, then printf will get into this address and then read the content and then print the data as a console output. That's actually arbitrary read because we supply the address and then print that out. So the capability that we have is that we can read a string using %s directive. Yeah. We can put an arbitrary address in the buffer and then read that as a string. So it's an arbitrary read. But the problem is that the string read will be terminated if the printf emits 0 character, because the 0 character is null byte, which means the end of the string. So if we have the value, this kind of value, 410041, this is character A and null and A, yeah, in that case, like it print out A, null, A, but it will print just A, because it will emit the A and this is 0, and then printf will regard that this is the end of the string, and then string print is end, because we print the string with the %s directive. But we don't give up. So to read the data in more consistent manner, even if we have the 0 value here, so we can read the data, and then there's a trick. And to read 4 bytes in like the 804A010, what we can do is like we can split the read in 4 addresses, so 10, 11, 12, and 13, and then we can refer this one as a 7th argument, 8th argument, 9th argument, and 10th argument. So if we print out 7th argument, 1 character, 8th argument, 1 character, so we will print out each character from each location, then we can easily identify like what will be the output. And then if you place this kind of a pipe like this, then you can also identify whether there's a value or not. So for example, if the data is a 1, 2, null, 3, then it will print out the 1 at here, bar, 2 at here, bar, and no data because it's 0, and then 3. So you can also like identify a null string from here. Yeah. And after understanding this, you can pound the next challenge, format string arbitrary read. So this is a similar thing that you need to guess the random number, but the problem is that the random number is now not on the stack. So that will be stored into the global variable area and as the variable random value. So you can get the address of this one from GDB. And then you need to guess the random value, and then that need to be matched with the value stored in here. So what your task is that you need to leak this value in the global variable. So how can you do that is like get the address of the random value in the global area from GDB. And then suppose that address is like 804A050, then you can formulate your format string as that value at the front of your buffer, then it will be shown up as the argument. And then you can put the $7 if the 7th position is referring to this one. Or in Palm script, you can just use a p32 to make this as like a string value. Yeah, integer as a string, binary string. Yeah, and then you can get the random number from the console output as a text string. Maybe you need to apply u32, or if the random value contains 0, then you need to use this kind of a trick. But at least you can get the some of the data from the random number, and then you can make the perfect guess. So we just learned how to launch arbitrary read. Then how can you do arbitrary write? We will use the very similar approach to like a launch arbitrary write, and then the just changing thing is like we change it the %s to %n, because %s is for dereferencing and reading the data, and then %n is the dereferencing and writing the data. So for example, suppose we need to write some of the values in this address. Then what we can do is like putting this address at the buffer, so we can see that that as an argument in the stack, and test it first with the $7p. It could be %8, %9, or %6, so please test it. And then if you can see the same value that you put here at the output, then you are good. And then change that with the %n. Then what this format string will write to this address. So the printf will refer to the 7th argument, which is this one, and then it will dereference this address and then store the number of character printed. So this will write a 4 to this address because it printed these 4 characters before meeting this %. Yeah. So we can at least write number 4. Yeah. But writing number 4 does not conclude the arbitrary write. So arbitrary write means that for the arbitrary address, so for example, right now we know how to write 4 byte here, but if we do it again and again, so maybe we can write a 4 byte, 4 byte, 4 byte, and so on. So we can overwrite like any kind of any length of the bytes if we repeat this. So we can choose our arbitrary address and then arbitrary length. But what about the arbitrary data? Yeah. So in this case, we can put 4, not the other values. Then how can you put the other values than 4? And to do that, we can use some tricks for printing some fixed number of the characters regardless of the argument value. For example, %10x. This will print exactly 10 characters regardless of the value of the argument in a hexadecimal format, 10 characters. %10,000x. This will print 10,000 characters exactly. And then this will print 2 to the 30 characters, which is many. Yeah. But in the one of the challenge, you need to you are asked to write the value this FACEBOC Facebook, yeah, into your your random number. So the random number will be initialized as a real random number, but using the format string variability, your task is to change this value in the global variable into this one. So it asks you to perform the arbitrary write. You need to perform write on this address and change the value to the specific one. Yeah. Then how can you write this value, Facebook? That value in hexadecimal is around 4.2 billion. So you can try to print this much of the characters, but no way. The problem is that the printing 4 billion characters is super slow. the printf function internally need to handle all these like characters. So if you supply like printing 4 billion characters, then your exploit would work, but it will be end up after a few weeks or maybe a few hours in our modern computers. Yeah, so it is slow. And suppose, so right now we are launching exploit and locally, so we don't need to think about that. But if you suppose this kind of the attack scenario is like attacking the server, then you need to download 4 GB for 4 billion characters. So that's another problem. And then most of the systems are now running 64-bit machine, and then they are using 48-bit addresses. And then some of the addresses that we are seeing is this kind of the big. And if you supply this number, then it's a super big number, and your exploit may not end in several years. So this is not the way that we can put arbitrary value, but please don't give up. We have a trick that we can split the write into multiple pieces with the smaller numbers. That is, suppose we need to write this number, Facebook, to this address. Then what we can do is we can prepare 2 addresses as an argument. So 2 addresses. So 804, A0, 10, and 12. So 2 bytes next to that target address. Then it will print 8 bytes. And what we will gonna do is so print some more bytes to fill up to BOOC. Yeah. So we will write the last 2 bytes first 2 bytes first, and then next 2 bytes at here. So we will write the 2 bytes at this address and then another 2 bytes at this address. So that's why I shifted the address by 2. And then because we have the 2 arguments, it already printed at 8 bytes. So what we need to do is like print a BOC minus 8 number of the characters with the %x. So that's this number. Yeah, and then use this argument to print out the store the value. So it will store exactly BOOC. So actually 0000 BOOC, this 4 bytes to this range. And then next we need to write the FACE, but we already printed the BOOC number of the characters. So the number of characters we need to print additionally is the face minus BOOC. So that's this number. And then we will use the next argument, not the same argument. Then this will overwrite the 0000 FACE to this range of the address. But it will overwrite some of the out of the range, but we will ignore that value. And then this will write BOC and FACE, so we can change the value of the global variable to arbitrary values. And then we can alter all these data, so we can actually write the arbitrary values. So maybe you catch some of the difficulties in doing this. So some of the subtle cases could be, so right now the second value, FACE, is bigger than the first value, BOC. So we can subtract this. But what if the second value is smaller than the first value? So can we overwrite 1, 2, 3, 4, 5, 6, 7, 8? If we cannot do that, we cannot say it as an arbitrary write. But we can do that. So writing 5, 6, 7, 8 is easy. So we will print out 8 characters, so subtract that by 8, and then apply %n. And then, so to write the 0x1, 2, 3, 4, we need to apply 0x1, 2, 3, 4 subtracted by 5, 6, 7, 8, but this will generate the negative number. And to avoid that, what we can do is like instead of the overwriting 1, 2, 3, 4, we will write the number of characters as a 0, 1, 1, 2, 3, 4, because we will ignore this carry. So we will focus on only for the 4 bytes. We will not care about like some of the additional bytes that we overwrite. So in that case, like we can change the number like this. Then this calculation, yeah, this is actually the 0, 1, 1, 2, 3, 4 minus 5, 6, 7, 8. So this is that number. Then that will exactly put the BOC, FACE, and then maybe 0, 1 for the next address. But we will ignore that. Yeah. And then we also need to handle like the 64-bit machines. Yeah. And then will there be any differences in 64-bit machine? Yeah. So suppose we need to write the FACE-BOC to this address, so 64-bit sum of the code address, data address. Then we will prepare two addresses as an argument, as we did, something like this, and then it will print 16 bytes. So we prepare BOC minus 16 with the first %x and then %n to this one. So this will print 4 bytes at here, and then FACE, so FACE minus BOC, this one, and then write that. Will this work? This will never work because take a look at this argument. Printf accepts a string as a format string. And then if we prepare a string like this, then printf will stop processing the string after meeting any kind of 0, because printf processes string, and string in C expects like a 0 as the end of the string. So because of this 0 byte, printf will stop processing this data, so you cannot use any kind of the data after this null bytes. So printf will ignore all these bytes. So you cannot use that. Then how can you avoid that? So let me explain that with you. Let me show you the example of the how can you avoid that by showing the example of the overwriting 0x1234567 to this address in 64-bit. So to write 5678, we need to prepare something like this. And then right now we do not print anything at the start, so we just prepare the values, a number of characters, the same as like the last 4 bytes, or the last 2 bytes. And then for the address +2, we will print out this value, but because the 1, 2, 3, 4 is smaller than the next value, so we will add 0, 1, and we will borrow the carry, and then subtract it, and then we can construct some of the exploit string like this. And then like you might need some of the padding, because like we will try to read the argument from the printf, but the printf will read the argument by the 8-byte granularity, 8 byte, 8 byte, 8 byte. So because this kind of the length could be variable depending on the what kind of value we would like to write. So you can control like the entire bytes, entire size of your format string as like the multiple of 8 to like a point some of the arguments that you will supply in the buffer. And then so in 32-bit, we put all the address values at the front, but we will do the opposite in 64-bit because the addresses are containing 0 values. So we will put all the format string part first, and then after having a padding, then what we will do is we will attach the addresses at the end. And then this will work because printf will process all the colored part and then also process AC1060 and then stop processing after meeting 0. But the interesting thing is like that our stack, the way of like we inject the data is like based on the read function, so it doesn't matter of the string. So that these values are still in the stack. Yeah. So although printf stops processing it here, so these values are still in the stack. So if we refer to the 10th argument, then it will go to this one, and the 11th argument, it will go to the 11th. And then another difference is that like the 1 argument distance is 8 byte in 64-bit. So then the reason why not 7, 8, 10, and 11 is like we have used 24 bytes here for the constructing the format string. So 7 will be here, 8, 9, 10, okay, and then 11. So the exploit sketch for the format string arbitrary write is as follows. So you need to get the address of the global variable from GDB and get the target value, and then calculate first and second value, and you can prepare like all the format string before attaching the address in 64-bit. Yeah. So in 64-bit, the important thing is like you need to put the addresses at the end. And in 32-bit, if the address does not contain 0, then you can put the address at the front. And then in 32-bit, if your address contains 0, then you need to put the addresses at the end. So today we learned how to turn format string vulnerability into sequential read, arbitrary read, and arbitrary write. So please work on the challenges for week 6, and we will have tutorials for the challenges introduced today via Zoom meeting. Thank you.